Hi everyone, welcome back. Today we are tackling the hello world of the high performance computing, matrix multiplication. While in the previous example, word add, it tested our bandwidth. The matrix multiplication tests our compute throughput. So our goal is very simple, to calculate C equals to A times B. So for each element in matrix C, we take a row from matrix A and a column from matrix B, and then compute the dot product. But before that, let us review some basic settings of the GPU. We have the concepts of grid. For each grid, we have some blocks, and for each block, we have some threads. Let's assume in this example, we only have one grid, and also the thread dimension in both X and Y are 32. Okay. Since each C element will be calculated by each thread, and if we assume the matrix dimension in X and Y are 1024, which means both NX and NY are 1024, and then we can calculate the block dimension in both X and Y direction. So the block dimensions are all 32. First, let's talk about the matrix mapping. So matrices are two-dimensional structures. So we use a 2D grid of the threads. In CUDA, we use a dim straight struct. If you go through the code, and you will find the dim straight here. Okay. So by convention, we mapped thread IDX docs X to columns. So we map this to columns, and we map thread IDX.Y to rows. However, computer memory is 1D. It is just a long tape of the bytes. C++ and CUDA use row major layout. This means consecutive elements of a row are stored next to each other in memory. That's very important. To map our 2D coordinates, row, column, to this 1D memory, we have used the standard formula. The index equals to row ID times width plus column ID. Okay, something like this. So row ID times width. Width is the width of the matrix plus the column. So note, if you come from a Fortran or MATLAB background, this is opposite to column major layout. Mixing this up is the most common bug in scientific computing. We can also imagine the matrix as a bookshelf. In row major, like C++, we store row 0, row 1, row 2. In column major, like Fortran, we store column 0, column 1. Since CUDA hardware is optimized for C-style access, we must strictly follow row major indexing to achieve coalescence. Now, let's zoom in. So for each row, we have to find the block IDX.Y times block dimension.Y. As we said, this is 32, plus thread IDX.Y. And for the column, we use a block IDX.X times block dimension.X plus thread IDX.X. So one way to memorize it, X for column, Y for row, right? We're going to analyze what happens inside the hardware during a single loop iterations. Let's look at a single warp. Okay. This is a 32 consecutive threads. Suppose we're calculating the first row of the tiles. So the thread idx.y is 0 for everyone, and we are all in row 0. But the thread idx.x range from 0 to 31. So thread ID compute the, in here, thread ID compute the C00, and thread 1 compute C01 up to thread 31. Let's assume the loop variable k equals to 0. First, let's look at matrix B here. Since k equals to 0, the index simplifies to just a B column. So the thread 0 requests index 0, thread 1 requests index 1, thread 31 requests index 31. Because the matrix B is row major, these addresses, 0 to 31, are physically adjacent in VRAM. So the memory controller sees these 32 requests and says, hey, this is a contiguous block. It merges them into one single transaction of 128 bytes. This is called the memory coalescence. It is the gold standard of the GPU memory access, and the efficiency is 100%. Then let's check about the matrix A access patterns. Again, assume k equals to 0 and row equals to 0. Okay, so this index simplifies to A0. So thread 0 wants A0, and thread 1 also wants A0. In fact, all these 32 threads in the warp want exactly the same element. So the memory controller handles this via the broadcast, as I show here. Okay. It fetches the data once and replicates it to all threads. So while this is fast in terms of latency, it is wasteful in terms of the bandwidth. We fetched a whole of 128-byte cache line just to use one integer. 4 bytes. Here's the real problem. Think about the next warp, the one calculate row 1. They will need to read the B0, B1 until B31 again. And the warp after that will read it again. So in these naive implementations, we're dragging the same data from the global memory VRAM across the PCIe bus or L2 cache thousands of times, while we are hitting the memory bandwidth, or we are moving data more than we're doing math. To summarize the access patterns of this baseline example, the matrix B gives us good coalescence, but we are rereading it constantly from slow global memory. The matrix A gives us broadcasts, but we are wasting bandwidth. How do we fix this? We need a way to load a chunk of A and a chunk of B into a local scratchpad, somewhere fast close to the cores, where we can reuse the data without going back to VRAM. This scratchpad is called shared memory, and this is exactly what we will implement in the future videos. Now let's back to the host code. There's nothing new here. So instead of writing a raw for loop to initialize our vectors h underscore a and b and c, we use the C++ standard algorithm generate. So we pass the lambda function that are syntax with square brackets to fill the vectors with random numbers. This is a modern C++ style. It makes the code cleaner and less error-prone. And then the most critical part of the matrix multiplication is the execution configuration. So as we said, there are 32 threads per block, and then we have 32 blocks, in each dimension. And then we use the CUDA built-in type dim3 to define our dimensions. The dim3 threads 3232 creates a block of 32 times 32 threads, this line. That is the 1024 threads per block, the absolute maximum limit for current NVIDIA architectures. So we are maximizing the occupancy of streamlined multiprocessors. And then for the grade, we calculate the blocks as n divided by threads. So n equals to 1024 and threads equals to 32. This divides perfectly to 32 blocks in each dimension. And dim3 blocks define the grade of 32 by 32 blocks. So in real-world scenarios, if n is not a power of 2, you must use the Selling division formulas. N plus thread minus 1 divided by threads. I think we covered this in previous vector add examples. Otherwise, you will crop the edge of your matrix. Then we launch the kernel matrix multiplications to parse the blocks and threads. The CUDA mem copy, similar to before, it acts as the global synchronizations. And finally, we have to verify our results. Still, you can compile the code, use MVCC, and then run it. Yeah, so that's our first example, also our baseline of the matrix multiplication.